So how we expand the dimensionality? Here's an example. Let's say originally we have these data points in 2 dimensions. Then we can create 4 dimensions as follows. Imagine we create 4 different multiplications this way. So we are using the original variables, but we are creating 4 different variables out of the 2 original that are just relying in the 2 original variables. So this is expensive. That's a problem. Every time we get a vector and we start going over all the possible combinations to produce this multiplication, it's going to take time. Imagine we have to do this for every single training point. But there's a trick. This is called the kernel trick, and what it does is create the same effect without actually doing this multiplication of all the possible combinations. So instead of really going and getting the vector in a higher dimension, we are just going to pretend that we are in the high dimension, but we just are going to use the original data. How? Through using the dot product. For example, we can see that if we create the dot product between 2 vectors that are already expanded, we get a result that could be easily determined by a dot product of the original vectors, but then to the power 2. So in other words, the trick says that if we don't actually need to see the vector in higher dimensions, but we only are going to need those vectors to calculate dot products, then we don't need the vectors. We can get the same result of high dimensional vectors dot product just by using the original dot product but applying the power 2 after we get the result. So in other words, we are saving a lot of time, because instead of getting to the modified vectors to make the dot product in where we spend big O n square per vector, we just need to calculate the dot product of the original vectors and then apply a transformation to the result. We achieve the same purpose, but in this case, we do not need to do anything to the original data. So in other words, we are saying that I can provide you with a high dimension result, but only if you never need to see explicitly the vectors in the higher dimensions. Okay, this is what I'm saying here, right? If we never need explicitly to see phi of x or phi of z, then we can use the kernel trick such that we apply transformations to the dot product result of the original vectors, and we are going to be working in a high dimensional space without being touching the high dimensional transformations per vector. So this is the main question. Will we need to see the high dimensional vectors phi of x or phi of z in the support vector machine model? The answer is no. Fortunately, we will never need to see a vector on its high dimensional version. We just are going to need dot products of them. Having that said, we just can use the kernel trick over the dot product of the original vectors, and we are going to have a model that is working in high dimensions. So let's see why. Here, we have the results of the optimization of the SVM model, right? The only difference is that instead of using x, we are using phi of x. In other words, we are assuming that we are going to need a high dimensional vector. Now we need to explore if we will need the dot product of the phi vectors, or at some point we need the actual phi vectors themselves. That would be a problem. So here we see that in this equation we are fine because we are just using the dot product between these 2 phi vectors. Same thing here. But we have one problem here. In this equation, to calculate w, we would need to have explicitly the phi vector of xi. In other words, we will have to calculate the high dimensional vector, and this would be very costly. But since that we only need the support vector machine to perform classification, we always need to multiply our w vector with the vector of the data point that we want to classify. In other words, we never need explicitly to know the hyperplane. We just need to perform the dot product to create the classification. So knowing that, if we get a new data point xt, we apply the transformation. In order to classify this data point, we're going to multiply this by this, and then we add this new vector here that is telling us that we need the dot product. So this is great, right? Because at the end, we can work in high dimensions without even knowing those vectors if and only if the only thing we need from the support vector machine is classification. But if someone tells me that she needs explicitly the equation of the hyperplane in higher dimensions, we are not going to be able to provide it. To conclude, the main takeaways we saw in the support vector machine model is that it is a classification model that aims to separate classes with hyperplanes by solving an optimization problem. It can handle non-fully separable classes by adding slack variables. But keep in mind that there is a cost parameter that we must set that is going to balance between the cost of the misclassification together with the margin. With the kernel trick, support vector machines can create nonlinear separations just by using linear models in higher dimensions. But recall that this is as far as we don't need explicitly the equation of the hyperplane, because we cannot access W, since it needs the explicit version of the vector represented in the high dimension.